Hello again everybody, it's James here from Flocode. Welcome back to video 3 of the Flocode Intro to Python series. In this video we're going to delve into some fundamental programming principles. I'd like to emphasize that this is not an in-depth exploration of coding or syntax. Instead, we're going to take a high-level, fast-paced approach to providing you with an overview of the essential concepts in the beginner Python landscape. This is going to help you understand how the various components fit together, especially in an engineering context. Don't worry if you're unable to grasp all of the nuances of the syntax during this video, because I do provide some examples just to show you generally how things work. But the primary goal is to introduce these concepts at a high level and plant some seeds in your mind and familiarize you with the 50,000-foot view of the Python programming landscape. So we're going to dig much deeper into the specifics in subsequent videos, but for now, let's just focus on building a solid foundation for your journey into Python. So let's jump into it. Computers are incredibly powerful tools and designed for one thing: solving problems. As an engineer, you're fundamentally a problem solver. You take in the complexities of terrain, the laws of physics, the constraints of materials, and you craft solutions. A bridge that spans a valley, a structure that can withstand the elements, or a road to connect a community. A lot of what we discuss in this section will be familiar to you through the context of your current experience with existing tools like Microsoft Excel or MathCAD, but these are also important fundamentals that we need to establish as we relate them to Python. Just as you wouldn't design a bridge without understanding the physics and mechanics involved, programming demands a new kind of engineering toolkit. You're going to swap the statics and dynamics of structural analysis for logic, algorithms, and data. And this is how you shape the structure of your solutions. Python will teach you a whole new fluency for problem solving, where you dissect complex challenges into clear, computationally solvable steps, which leads us to our first core principle, and one that you're already very well versed in, and that is problem definition and decomposition. Just like any successful engineering project, the foundation of effective programming is clearly defining the problem. You're not going to start pouring concrete before you carefully survey the site or calculate the material requirements. In the same way, a computer needs precise instructions. It can't understand vague goals. It thrives on clarity and specificity. Let's take the example of designing a beam to support a load. To a human engineer, that statement implied a whole process with many different steps and variables. You got to consider the applicable design codes, the material options, the beam geometry, what safety factors you're going to use. A computer can't make any of these leaps intuitively. We must reframe the problem in a programming language. So something like, given a specific set of material properties, a defined load, a span length, and based on a certain set of sequential logic and algorithms, calculate the minimum required dimensions to satisfy a code-mandated stress requirement. It's a big mouthful, but that's step by step exactly what we need to do. The initial problem seems insurmountable to a computer, and that's where decomposition comes in, which is going to be your most powerful tool. It's basically the process of breaking down a large, complex problem into smaller, self-contained ones. Can we isolate the calculation of the beam span? Can we define the loads separately? Or what about determining the section modulus needed to resist the bending moment? Each of these subproblems is far more manageable for a computer to solve. And I know this might sound very obvious because you're already familiar with this concept, but abstracting this type of thinking to a variety of engineering problems can become quite nuanced. So that's why we're beginning with the basics. Think of programming like this. You translate the entire solution to your problem into a sequence of precise mathematical and logical operations. When the computer tackles each smaller task individually and combines the results, it effectively solves the complex problem that you initially posed. I think you get it. Sounds so simple when I say it like that, and it certainly can be, but usually it's not. Let's talk algorithms. An algorithm is the heart of any program. It's a recipe that tells the computer exactly how to solve a problem or to complete a task. And just like a good recipe needs the right ingredients, it also needs the correct order of operations to be successful. You don't put a pizza in the oven without any cheese. Think of a familiar engineering task like calculating the stress in an element. This is a simple fundamental formula with a single output. Stress is equal to force over the area. So formulas directly calculate a single output, but algorithms can encompass multiple formulas and logic and even create new formulas on the fly to adapt to input data or results. We can turn this simple formula into an algorithm to make it a little more robust and useful. For example, we're going to add a couple of bells and whistles, just like a check to ensure that the area that we input is a positive value, and it's going to give us a warning if it's not a positive value. And then we're going to add a printed output statement to verify our result. So I'm not going to get too deeply into the code here, but we're defining a function called calculate stress with two inputs, force and area, and if the area is less than or equal to 0, we get a warning message that says invalid area, area must be greater than 0. So if our area is positive, then it simply returns the result of the calculation, force over area. A formula is rigid. An algorithm can adjust its behavior based on conditions, which makes it much more versatile. And the true power of algorithms comes in their versatility and repeatability. Imagine needing to calculate bending moments at multiple points along a beam, or needing to modify the design to analyze different types of loading scenarios. So just like you might update a recipe by altering the quantity of one ingredient, you can change the input values for an algorithm, like the magnitude of the force or the location of a force. And then your computer will execute the same steps to produce a new answer. Algorithms can manage intricate decision-making processes. Think of optimizing your beam design. An algorithm can iterate through standard sizes or geometric configurations, which assess each against stress limits or weight, and if any of these options fails the check, the algorithm can have rules in place to discard a certain size and move on to the next check by increasing the beam depth or web thickness or some other predefined parameter. Algorithms will be the building blocks of your computational problem-solving skills. Once you grasp the idea of translating well-defined engineering problems into these step-by-step recipes, you open a very powerful new chapter in your design and analysis capabilities. Let's talk variables. Just like a physical toolbox holds your tools, variables are the storage units within your program for the data that you need to solve your problems. They're kind of like customizable containers with some of the following key aspects. Most importantly, the name. You must choose a descriptive name that directly relates to the concept that they represent, like beam length, steel grade, steel density. This makes your code self-documenting and so much easier to understand for yourself and anyone working with it. Usually it's the future version of yourself 1 week or 2 weeks down the line where you completely forget what you did if you're anything like me. Next is data types, which means the variable can hold different types of data. It can hold numbers for measurements or forces, and those numbers can be integers like a whole number, or it can be floats, which means a decimal. Another data type is text, which means names, labels, IDs, attributes, or even entire sections of text or reports, paragraphs, you name it. Next, you've got Boolean values, which is a term used for logical conditions, which essentially checks if a statement is true or false. Very handy for creating a useful fork in the road in the logic of your calculations. The next concept is value, and this one's pretty straightforward. This is the actual data that the variable stores, and it can be changed throughout your program as calculations progress. And this is the feature of a dynamically typed language. But a value is 5 meters. If the beam is 5 meters long, the value is 5. So why do variables matter? Well, First off, flexibility. They allow us to easily adjust and experiment with different parameters. If you need to analyze multiple beam spans, you just update the beam length variable and rerun your calcs. Or even better, you can assign the variable beam length to a list of beams with different lengths or a database of beams and their associated properties. So as you can imagine, variables can become these fractal pieces of data which can hold one value or many values or even a huge table of values. We'll talk about that later. Readability. Imagine trying to keep track of raw numbers in a complex formula. Well-named variables make your code so much easier to read and understand and debug. We want to spend our time focusing on the logic and the process and not getting bogged down in the numerical data. This is the cornerstone of thinking Pythonically. Finally, organization. Variables bring structure to your calculations. By assigning specific variables to force, dimensions, material properties, and other relevant parameters, you can create a clear and organized framework for your analyses. This kind of structured approach maintains a clear overview of your computational model and ensures that each component of the project is accounted for and it can be easily adjusted when you need to. So let's bring this to life with an example. Say you're calculating the deflection of a simple beam with a load at the center. So you can see here in this image we have a simply supported beam, a point load at the midspan, and we want to check what the deflection is. You got the classic deflection formula PL cubed over 48 EI. And then you got some variables represented down below, and you can see that they're pretty self-explanatory. You've got the beam length, you got the load, you got your Young's modulus, you got your moment of inertia as I, and you got your deflection value. So it's important to choose these meaningful names that reflect the concepts that you're working with. And you need to be careful of data types and just ensure that your calculations are using them correctly. You don't need to worry about this too much now because we'll dig into the syntax more later. I'm really just flying through this stuff to give you a high-level overview. Variables are the fundamental building blocks to construct your algorithms, but they're only one piece of the puzzle. So how do we logically operate with all of these variables? Well, that's the next topic. Operators, logic, and control. Operators form the core of how you perform computations in Python. Basic arithmetic operators like plus, minus, multiplication, division, let you work with numerical data for everything from structural analysis to fluid flow. And beyond that, you have comparison operators like greater than, less than, equal to, which allow you to test conditions which are essential for decision making throughout your code. Is this particular load within the allowable safety limits? Does this length exceed a certain value? Python's operators empower you to translate your engineering judgment into code that automates evaluation and actions. Let's talk a little bit about logic and understanding how to program your engineering decisions. Logic operators, which include and, or, and not, allow you to build complex conditions that reflect real-world scenarios. So say you're selecting some materials. Is this strong enough and cost-effective? A logic operator lets you express these nuanced requirements within your code. Conditional statements like if, elif, and else, which are Python-specific keywords, they can direct your program's actions based on these types of evaluations. It's like embedding your problem-solving process into the program and guiding how Python should calculate for different scenarios or to generate different design alternatives. Control flow tools govern the order of Python, how Python executes its instructions. There are looping structures, which include keywords like for and while, which let you iterate through calculations for every beam in a specific frame, or to recalculate a model as design parameters change. This makes repetitive yet crucial engineering tasks far more efficient. And the ability to control execution lets you design code that aligns with how you think through your engineering problems, ultimately automating the steps to focus on the results and not the process. So There are more advanced operators, but we'll cover those when it's appropriate. Some notes here on the order of operations in Python. It's the same as the standard mathematical model. You have a formula, and the first thing that executes is whatever is inside the parentheses. Then next becomes the exponents, followed by multiplication or division, followed by addition or subtraction, and then you get your result, which is just the same as calculators and Excel as far as I'm aware. So this whirlwind tour has covered the essentials of programming, and at this point the concepts might still feel very abstract, like looking at a set of drawings missing a lot of different components. And the principles that we've discussed will translate directly into the fundamentals of Python code when we begin to learn it. And as we progress through the Flocode Essentials course, these concepts will snap into focus with tangible examples from your own engineering experience. You're going to see how to automate calculations, iterate through solutions, visualize and analyze data, and a whole lot more. The best part is, as you learn to code, the way that you view engineering problems themselves may even begin to shift. It's a very strange experience, but it's certainly worth the effort based on my own personal experience. So thanks for listening. This was a long one, and the next one we're going to talk about is the community. So see you there.